This video, we're going to discuss the concept of entropy. The entropy of a system is a measure of how spread out or dispersed the system's energy is. Put another way, the entropy is a measure of molecular randomness or disorder. The more random or disordered a system is, the higher the entropy for that system. Now we can calculate the entropy of a system using an equation given by Boltzmann, where S is the entropy of a system, and we could be talking about, for our system, the entropy of an element, a molecule, a compound, or a more complex chemical reaction. K is a Boltzmann constant. You can see that value here. The units of the Boltzmann constant, and therefore the units of entropy is given in joules per Kelvin. And our constant comes from dividing the gas constant by Avogadro's number. Ln, of course, is a natural log. And capital W is the number of possible arrangements or microstates for a system. So the more microstates or system, the more microstates for a system, the higher its entropy. Since K is a constant, the bigger this number, the bigger the entropy, the higher the entropy. So what do we mean when we talk about microstates? Let's talk about that for a minute. Let's say we have two flasks separated by a stopper, and initially all of the gas molecules are in flask A and none in B. What's going to happen when we open the stopper? Well, of course, we know that the gas molecules will spontaneously move from A into B. Not all of them, though. They'll begin to move from A into B until the molecules are evenly distributed. Now, this process is not a static process. We will reach equilibrium where the molecules are moving back and forth, but at the same rate. So we reach an equilibrium, but the key here is that the molecules are evenly distributed rather than all of the molecules staying in A. So why don't they all just stay in A when the stopper is open? Or why don't they all move into B? Or why don't just a few move into B? Why do we get a relatively even distribution? Why is that? Well, it depends on the number of microstates. When the molecules are evenly distributed, like we see over here, there are more possible microstates, and therefore the process is more likely to occur. So the more microstates, the higher the entropy, the more likely the process is to occur. But again, how do we know that there are more microstates over here when they're evenly distributed compared to over here when when all the molecules are in one side or the other? Let's look at a little bit simpler example to help us illustrate this. Let's say we had just 4 gas molecules. You can see those here. And the 2 flasks were open. The gas molecules can move back and forth. If all the 4 gas molecules are on the left side, we have 1 possible microstate. If one of the gas molecules moves to the right side, it could be the blue, the yellow, the red, or the purple. Either way, we would have 4 possible microstates. So this is 4 times more likely to occur than them all being on one side. You could see more microstates, there's higher probability. Well, what if 2 gas molecules moved over to the right side and 2 on the left side? Well, then we would have 1, 2, 3, 4, 5, 6 possible microstates. So when we have an even distribution with just 4 molecules, it is 6 times more likely to occur than all the molecules being on the left side. So there's more possible microstates. It's more likely, probable to occur. And again, we could continue on. We could have 3 on one side, 3 on the right, and 1 on the left. Or we could have all the gas molecules on the right side. What I want you to appreciate here is that each of these arrangements, each possible arrangement, is what we call a microstate. The more microstates that are possible, the more probable that arrangement is. So if we look at what are the odds of all the molecules being on one side or the other? Well, there's 1, 2 possible microstates or arrangements. So the probability that all the gas particles would be on one side or the other is 2 out of a possible 16. So we have a total of 16. So that's not very probable. If we look at the probability that the molecules are evenly distributed, well, then we have 6 out of 16. So it's much more probable that the molecules would be evenly distributed. Now, 6 out of 16 versus 2 out of 16, that's not a huge difference, but this probability the difference in probabilities increases greatly, as I'm sure you could appreciate, the more molecules we had. So if we had 1,000,000,000,000 gas molecules over here, then having them all on one side and none on the other, we would have it would be almost totally improbable that that would occur. The likelihood that all the molecules would be evenly distributed when we had a lot of gas molecules would be very, very great. So the number of with more microstates possible, there's a greater probability that the molecules will be evenly distributed. So again, back to our original example. Here, the number of microstates on the right is much, much greater than the number of microstates over on the left. And so because of that, there's a much higher likelihood, that the molecules will be evenly distributed. And so really that's what entropy is. Entropy is a probability. The higher the probability, the higher probability generally occurs when there's more randomness and disorder because there's more possible microstates. So all of the molecules being over on side A is possible, but it's almost incredibly improbable when you have a lot of gas molecules. So put one last way, the more probable states, the more probable state is the one with the largest number of possible arrangements or microstates. So since we have more microstates, this is much more probable and more likely than over on the left. So let's look at microstates in respect to individual molecules and elements. An individual molecule has a certain amount of entropy. We could look at tables. Your text has an appendix with the entropy values for lots of different elements and molecules. For example, liquid water has an entropy value of 69.91 at a certain temperature, at 25 Celsius. So where do we get these values from? How can individual molecules have entropy values? So some molecules, individual molecules have entropy values. Some molecules have more entropy than others. How can we compare the entropy of individual molecules? How is the entropy of an individual molecule determined? Well, it goes back to our microstates. The more microstates a molecule can have, the more entropy it has. But microstates are not only described by the physical distribution, like we showed you with the gas molecules, either on the left or right, but microstates can also be applied to energy or electron distribution. So let's take a minute to talk a little bit about that. For example, here are our noble gases, helium all the way down to xenon, and you can see that we get a larger molar mass or atomic mass in xenon compared to helium. So for comparable structures like these noble gases, the entropy increases with increasing mass. So xenon has a much higher entropy value than helium. And that's because xenon has many more electrons, and so the electrons can be arranged in more possible microstates. And so there's more possible microstates in regards to the electron distribution for xenon, and so xenon, being a larger atom, will have a higher entropy value than helium. Another factor that helps determine the entropy value of a molecule is the number of bonds it has, how complex of a structure it is. Molecules with similar masses, the more complex the molecule, the more entropy it has. So here we have carbon monoxide and C2H4. They both are about the same molar mass or atomic mass, but C2H4 has a higher entropy. And that's because there are more bonds. And so again, a chemical bond has energy. And so there's more energy in this molecule and more ways of distributing that energy. Let me show you an example to help illustrate that. Let's compare the entropy of two molecules, fluorine, F2, and O3, ozone. For fluorine, which has just two atoms bonded together, you can see here's one fluorine bonded to another, the energy can be distributed in certain ways. This bond, the atoms that are bonded together, can stretch along the x-axis, so they can distribute their energy in a certain way here. And they can also have rotation about the bond, and you can see that down here. So the more stretching and rotation that a molecule can have, the more entropy it will have. So fluorine has a value of around 203 joules per Kelvin, its entropy value. If we compare that to ozone, ozone has three atoms bonded together. So there's more bonds, and so more ways of distributing that energy. Again, the bonds can stretch, like you can see here in the first one. Only one bond can stretch and the other be contracted, so they can have these microstates, or they can both stretch at the same time. So there's more microstates, the more atoms that are bonded together. And we also have the rotation about the bond. So ozone has more atoms bonded together, more bonds, and so there's more ways that the bonds can stretch and rotate, and so there's more microstates that the energy can obtain. And so ozone will have a higher entropy value than fluorine because of the complexity of the molecule. Here's a couple of other examples how molecular complexity increases, or how entropy increases with increasing molecular complexity. You can see CH4 methane and its entropy value. If we start adding carbons and hydrogens, again, there's more bonds, more stretching, more rotation about those bonds. So there's more microstates for the electrons and the energy to obtain. And so the entropy increases as we add more molecules and bonds. So as we add more bonds and bonds and atoms in a molecule, that entropy of that molecule will generally increase. The phase of a substance also affects its entropy. A substance that is in the solid phase will have lower entropy. In the liquid phase, it'll have more entropy, and in the gas phase, it'll have even more entropy. You can see the entropy of water in the liquid versus gas phase. It's much greater in the gas. Same thing for bromine. And of course, that's because the molecules are free to move about more. There's more randomness, and so more possible microstates when the molecules are in the gas phase than when they're much more structured in the solid phase. And again, more microstates equals more entropy. The entropy of a substance also increases with increasing temperature. So at higher temperatures, there's greater molecular motion. There's more distribution of the energies, more randomness, more possible microstates, and of course, higher entropy. And of course, the opposite is true. At lower temperatures, there's less molecular motion. The energies are more narrowly distributed. There's less randomness, fewer microstates, and therefore lower entropy. Now, the entropies of a substance that are ionic compounds depends on Coulombic attractions. So what's that? That's a fancy word. Basically, the stronger the attractive force between the ions, the lower the entropy. So here we have Mg2 plus and O2 minus. These are more highly charged ions, and so they're going to be stuck together more tightly than something like Na plus and F minus. The more tightly they're stuck together, the more tight or the higher the attractive force, the fewer possible arrangements, the fewer possible microstates, and therefore the lower the entropy. So you can see the higher the charge on the ionic compounds, generally the lower the entropy, and the weaker the charge, the less the attractive force, and the higher the entropy, because the ions are going to have more movement and more possible microstates. So in order to compare the entropies of different substances directly, we need to be sure that they're under the same conditions, all at the same temperature, all at the same pressure, etc. And so generally when we measure entropy, we measure something called the standard molar entropy. This is defined as the entropy of a pure substance under standard conditions. Standard conditions under thermodynamic conditions are described as 1 atmosphere of pressure, 1 mole of a substance, and our temperature must be 25 Celsius or 298.15 Kelvin. And again, you can see back to this table, all of these values here are what we call standard molar entropies. These are the entropies under standard thermodynamic conditions, so we can directly compare them. For example, we can see that O2 has higher entropy than N2. And again, if we look at the number of electrons, the mass, that would make sense. So let's look at a few questions. Pause the video and see if you can answer this question. Okay, so which substance has the greatest standard molar entropy? Well, if we look at these, they're all in the gas phase, but this molecule here, C4H10, there's much more atoms that are bonded together, so there's more bonds. So there's more stretching, more rotation, more ways, more microstates that the energies in the bonds can distribute themselves. So we have E should have the highest possible entropy. Take a look at this one. Pause the video and give it a try. Which one has the lowest entropy? Well, if we look at these, look at the phase. Here, MgCO3, magnesium carbonate. This is a solid. Solids have much lower entropy values than liquids and gases, so it should be C. Let's look at one more. Pause the video and give it a try. So which of these would have the largest entropy? Well, we can probably rule out the solid. Hydrogen iodide, this is a gas, and it's also the largest molecule, so there's more electrons here, and so the more electrons they have, the more possible arrangements, the more microstates for the electrons to adopt, so E should be our answer there. So be sure that you appreciate the concept of entropy, understand what we mean by microstates, and how we can determine the entropy of a molecule.